Hello class, this is Ms. Riggins with today's video on hyperbolic functions from chapter 14, section 6. Hyperbolic functions are a special type of functions that appear frequently in engineering, and they involve e to the x and different transformations of e to the x. And this two particular functions seem to be appearing frequently, and so they named them hyperbolic sine and hyperbolic cosine. And I'll explain why it's sine and cosine instead of something else. But let's take a look at these particular two functions. The first function is 1/2 e to the x, and the other function is negative 1/2 e to the negative x. And let's look what happens when we add them together. We come up with our own special function, which can be found by adding the two functions at each point. And so we end up with something that looks like that. And then we also have another function which is found by subtracting the two functions. We'll make that minus. And it looks like this. Now some of you may be saying, oh, that looks exactly like a parabola. And it does look like a parabola, but it's actually not a parabola, and it's not described by a quadratic function. And you can see why, because this function is based off subtracting two exponential functions, e to the x. So let's define what the functions are named. So hyperbolic sine is basically called sine h or sinh, and it's the result of adding either e to the x plus a negative e to the negative x all over 2. And then the hyperbolic cosine, which is cosine h or cosh, is the result of adding the two functions, e to the x plus e to the negative x over 2. So, okay, let me clarify. In the original graph, I used e to the x and then over 2 and then negative e to the negative x over 2. So this is kind of like I added the two different functions I talked about earlier. And then when I subtracted the two functions, that minus a negative became the positive. And that's how you have the cosine of h of x. So just focus on these and you can see. Now, if you remember, when I subtracted the two functions, I ended up with something that looked like a parabola. That's actually not a parabola, okay, but it looks something like that. Of course, I can draw. Where the other one, when I added, it looked very similar to a cubic function. And that's because as x goes to infinity, this e to the negative x gets really, really small, and you have something that looks like e to the x as x goes to infinity. And when x goes to negative infinity, then this value gets really, really big, and this value gets really, really small, and you have something that looks like negative a really big value divided by 2, which goes to negative infinity. So this actually looks like e to the x, except right here in the middle, when you have where these values are very close in numeric value. Okay, and over here, when x is very positive, e to the negative x goes to 0, and we basically look like e to the x over 2 on this side. And when x goes to negative infinity, then this becomes really, really big, and this becomes small. But because this is a positive value, it ends up looking the exact same on this side. So this is a symmetric graph. You know, if I could draw, you could see it would be in perfect succession. It is a symmetric graph as well. So these are the sinh and cosh functions, and they are the hyperbolic sine and cosine. And then, of course, because they're related to sine and cosine, then tangent, or the hyperbolic tangent function, is a result of dividing the two, sine divided by cosine, which ends up being this numerator divided by that numerator. Okay? So this is their own special set of functions, and it's named as such. I suggest you memorize these functions and know the difference between the two. So the question is, how do they look? And I included a graph to explain how they look. This one right here is the hyperbolic sine. Okay. And this over here is a hyperbolic cosine. And then over here is a hyperbolic tangent. Okay, if you want to get an idea of what they look like. So why do we use sine and cosine? Well, before we get to that part, the reason why we use sine and cosine, before we get to that part, I want to talk about identities. And I put identities in quotation marks because these are really not trigonometric functions. But since we're treating them like they're trigonometric functions, then they have some type of trigonometric identities. And just like we have that sine plus cosine is equal to 1, in this case, because of how cosine of h and sine of h, or sinh and cosh, are defined, cosine h squared minus sine h squared is equal to 1. And if you want to know why that always works no matter what x is, you can go look at the book, because in that section 14.6 they have that proof. Okay? So, and that's going to be helpful a little bit later on. So let's take a look at why they're related to sine and cosine, and why we call them hyperbolic cosine and hyperbolic sine. Well, if you remember that a way to parameterize a circle is using the relationship between cosine and sine. And as t changes, the x and y values of this function also change. And we use cosine and sine to parameterize this circle. And t can go on from -infinity to infinity, and it will keep representing this circle. And if we want to represent a hyperbola, we use secant and tangent. So as t goes from negative pi to pi, you can see that, negative 2 pi to 2 pi, we can see that it looks very much, it travels along the hyperbolic branches, okay? But there is another way that I can define this hyperbola parametrically, and it doesn't involve secant and tangent, but what it does involve is cosh and sinh. Okay, so if I define cosh and sinh, and then I go over here, as you can see, it looks like it's making a branch of a hyperbola. So let me return the original hyperbola, and as you can see, the dot for cosh comma sinh is traveling the right branch of the hyperbola, and the branch for the left branch of the hyperbola is being traveled for the parametric equation negative cosh and negative sinh. So I have another way of defining a branch of the hyperbola. Instead of using secant and tangent, I can use cosh and sinh. Okay, and so it seems like that's why they named it these functions. And of course, I can change this function to h of e to the x. E to the x e to the x plus e to the negative x all over 2, and I'll get the same situation. So let's take a look at that. So here I changed it to, now we have the actual defined value of cosh, which is e to the t plus e to the negative t all over 2, and the exact value of sinh, which is e to the t minus e to the negative t over 2. And as you can see, if I replace the original parameterization of the parabola, it follows the branch, the right branch, i.e. the positive branch. And if I were to change it to negative, it would follow the left branch. Okay. So let's see. As you can see, it's following the left branch as well. So that's how we get cosh and sinh. So let's formalize or summarize what you need to be able to do for the skill. So you should definitely know how to be able to parameterize a branch of the hyperbola using the hyperbola functions of cosh and sinh. And you can use this notation, because this notation basically is the same thing as this notation, or you can use this notation. Both of them are representative of parameterizing a branch of the hyperbola. And again, this is only the right branch, and if I want to parameterize the left branch or the negative branch, I place a negative in front of each of these to be able to parameterize the left branch. So you need to be able to do that. You also need to be able to use the identities of the identity that we talked about in certain situations, and the home learning assignment problems will help you with that. And I think that's about it. So you need to be able to parameterize a hyperbola using cosh and sinh. And you need to be able to use the identities, and you need to be able to recognize the graphs and the respective equations for each of them. All right, I hope you enjoy it. And did I say skills test? I didn't mean skills test. I meant VA. Okay, talk to you later. Bye-bye.